First, well, thank you for the opportunity to present here. Hopefully it's really fun. The talks are amazing. Um, and yeah, during the presentation, if I like it, it's particularly this presentation is more like a conversation than a presentation. And if you find a way to interrupt me and ask questions, the better. Uh, I know that virtually is like a little harder, but let's try to go. What I'm going to talk is for the last couple of years, I've been using particular Scala to build the financial systems, and it's an interesting topic I like. And most of this presentation is basically the things I wish somebody had told me before starting working, and so I could avoid some headaches and problems. Right now I'm working on building like an exchange for crypto coins futures, and that's a really interesting challenge. We are aiming to be like a regulated exchange, and one of the fastest and solid exchange around. And it's a very interesting challenge that we are facing now. For that, for the core of my system, we are using Scala, and trying to move and use as much as functional programming as possible. I also worked for kind of a year for a Wall Street bank that actually has the office in Times Square, but is called Wall Street also. So let's talk a little about like using functional programming to build financial systems. But really, it's kind of like a very loose term. That's not really formal definition of a financial system. But here we're kind of talking about basically any computer system that deals with money and or used by a big bank. Usually deals with money, or it can deal with risk, calculating the risk of that money. But one of the main characteristics of this is people get really nervous if something goes wrong, because there is a lot of money on the line. So there is a lot of pressures to get things right from the start. That means a lot of challenges. Most challenges are common to many systems, but most of the time we deal with a lot of data, huge volumes of data. It's not Google level of data, but you have a lot of changes. The logic is really complex because financial products most of the time are kind of have a complex logic to calculate values and everything. Like you have derivatives of derivatives of derivatives, and then you have to calculate the risk that involves like taking all basically the speed and deceleration of movements of some variables, and you have to do all these calculations for this huge amount of data very fast. Depend even if you want real time or even end of the day. You have to have the answer at the right time, because either it will cost money, or even you will get out of you will get on the regulators' site. And also very important, obviously, correctness. All these systems have to like be exact, because we don't have the luxury to use like to be eventually consistent, or yeah, your balance will eventually appear in your account. I mean, there's a timeline, and people get really nervous if things don't match, for a lot of reasons. Well, like where's my money, or where's how much exposure we have to this risk. We don't have the luxury to like. I mean, some systems, if you lose like a user click, or you can just skip that and use the newest one, retry. Here you have to get the right result at the right time, and that makes things interesting. I would say that is not unique set of challenges, but there's a lot of pressure to get all the things right. Why? Because yeah, you can make people lose money. You can get fined by regulators. You can go to jail if you lose money and you know where where it is, or either, I mean, you will you see it every time, and basically crypto is kind of a shock for that. I mean, a lot of things are like, you don't know if they're really money missing or somebody stole it, because I don't know, and nobody knows. And yeah, I think if things get really wrong, you probably can go to jail because of that. So that's an interesting set of challenges. And to tackle that, you want the best tools available for this. You want your programming language to be fast, secure, you want to be productive. You want to trust your code as much, because even if you test all the test cases you think, I mean, there's a lot of things on the line. And for me, basically, I choose functional programming. And this why I choose it. Actually, I use Untitled functional programming. There is a whole line of Lisp derivatives, Lisp scheme, closure, or even you can do functional programming in JavaScript. I mean, also this reason ML and everything. But we want Untitled functional programming. But yeah, seriously, why why go through all the pain of finding a sophisticated compiler, writing all types, deciding all things? What I'm looking for, I mean, what we're looking for with this, I mean, they're all things are these reasonable things. Probably, I mean, it could be trivial for some of you, but we are looking for correctness. For that, we need to use sophisticated type systems. I mean, not the old C++ type system that with 5 types and a couple of unions. We want something that it can carry a weight. It can basically we want, at the end of the day, we want be able to prove things with the type system. We want composition. We want to build our systems based on functions we know they are working fine, and we should be able to compose this function into something that works just like the composition without worrying about having to test everything again, because there is an undefined combination of things that break. And at the end, other thing we basically I use a lot is data streams. So what is called also in other places reactive systems. Basically, we have a constant stream of data. We need to analyze that, calculate values based on that, produce results all continuously. And I want a paradigm that supports that easily, that make that code as easy as possible to read. And I found out like functional programming for that is amazing. You can really be concise and create a code that is readable and incredibly performant, because all the managing of the pagination and resources is basically calibrated at runtime. So that's kind of my main justification of why I'm using functional programming for all this. And let's go a little about for each topic. in this case, correctness is one of the most important things. I want to trust my code. I want to be able to basically, if compiles, it works. It's kind of a joke, but sometimes you trust the code because the way you write it, the way you have your functions, your type signatures, you know that it's very hard to screw things up if you put things in the right place. And in this case, we basically base our correctness into the type systems. And with that, I want to do a small digression. Initially, when I started code like this, okay, this is Scala, it's okay. Code like this was relatively normal for me. Basically, I'm just creating a function that initiates a transfer, have the user ID, the original user ID, and the target user ID, the asset that it will be part of the transfer, and the amount, and that will give you some results. After a while, and probably this change was mostly for me in the last year, I've realized that this is a horrible signature. There is things that I should not do this. This is a source of problems. And I decided to change that, and I actually got very good results. Since, okay, this is virtual, just think about it, the things you don't like about this. And if you want, you can post something on the chat or whatever. Actually, I will go back to this, but for me, one of the main things is it's very easy to swap, like put the wrong value here. In the, maybe you change the signature and you put the asset first, and then now you're trying to use an asset as a user, and things will break, and you have to write a unit test. You don't know where it fails. It doesn't prevent to write the wrong code. And also, this is we are using float for amount, and this is a complex area. That takes me to representations of money in computer systems. One of like the first gut impulse you have, and especially if you were working like with old machines and smaller machines like me, I started with a ZX Spectrum like long time ago. You say, okay, money is not really an integer. It can be, it has decimals, it can be a float, but float has its problems. It's a really interesting compromise. It's great for like calculations, complex calculations, but it has, obviously, because it tries to represent the reals are infinitely dense, and we have a limited amount of memory. This is a special representation that make compromises. Basically, you select, by the way it's created, you selecting different points, and if your value gets close to that point, okay, that's the representation, but it always has an error. That error has to be propagated and everything. And the problem is, it's like you can use it, but you have to be aware of where is the error, what are you doing in your calculations, right? The thing is, it's very easy to run into problems. I mean, you can say, okay, float is a very bad idea. It's only, I don't know, I think at this point it's like 32 bytes, or depends on your infrastructure. Let's use double, but even with double, you run into problem. This is a very simple calculation, right? 1.03 minus 0.42. But what is the result if you use just a very precise type of floating point is double? Even Scala or Haskell will give you this result. That's clearly not correct. Imagine if you start accumulating this rounding error will start propagating. So we should not use float or double. I think it's this kind of my recommendation. Never, 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 never use floating point for money. Unless you know what catastrophic cancellation means, but still, I mean, catastrophic cancellation is when you start propagating your error, and at some point the error is greater than the actual precision of the value. It's very easy in floating point to reach that situation where you have a huge number, you add a very small number, and then you subtract the huge number. Because the way error propagation works, you take out the biggest error in the sum, and then you have an error range that is greater than the value you have. That means that result is useless. And it's not that hard to get yourself in that situation if you're like have a long running process accumulating values. In some cases, I would say double is fine. In many cases, still you have the problem you had before, so it's not that fine. It's just like floating point is great. It works great for like mathematical calculations, sine, cosine. It's great to guide missiles to the right place. That probably was invented for that. But for accounting and dealing with money is not the best option. In Scala, Java, and in Haskell, you have like big decimal. I mean, you can try to invent your own format. We use, in some cases, we use just integer, and then have somewhere else the precision, that a fixed precision. But then you want to change your precisions, and then okay, you decide, okay, well, I will create a small struct that carries the value and the precision around, and basically you have just reinvented big decimal. You have it available in Haskell, Scala, Java. And works really great. I have also big decimal includes the correct rounding. A long time ago, I had a system that one of my colleagues had used. I think it was my colleague, or probably was me. I don't know. No, was using float for doing some calculations, or double, and one of the users complained that if you put the same numbers in Excel, it gives you a different result. And since from the business side, Excel is the golden rule, I changed that to big decimal and use what is called like bankers rounding, that basically even out the rounding from one place to another. So at the end of the day, everybody has the same rounding error, and it give you the exact same results as Excel. So the first recommendation is, again, never, never, never use floating point for money. For ratios and proportions and everything is fine, but for accumulating money is problematic. You can use it, but you have to prove that you're giving the right result in the right error range, and that means a lot of doing like paper calculations, and so probably it's not really that worthwhile. Maybe if you're hunting performance, but yeah, you have to prove it that you're giving the right results. So my recommendation is, again, it's easier to say never and figure out the rest. That's another thing that was wrong in the initial signature of that code. If I go here, I should have it. That users and a set are just strings, and strings can be anything, and it's very easy to mix up values, and we want to write our code in a way that it prevents you silly mistakes. So there's one thing I started doing like just relatively recently, and I'm kicking myself. I should have started this a long while ago, using IDs, type safe IDs. Basically, is just in Haskell, just a new type, or in Scala is a like ID that takes a type parameter and extends any vol and store a string, and you can use opaque types. This is something that at runtime, it's just a string. It doesn't cost anything, but for the compiler is something different. And so you are sure that you're not mixing up user ID and then a set ID. That will prevent, I actually found that I started doing this in the project last year, in the project I'm working right now, and I found that like a weird, very complex and hidden bug, because at some point we are missing. I was mixing like a set ID and a book ID, and there were actually different things, and I haven't never found it. Either when it failed on production, or but with the compiler, with all this, was very easy to find. And really, when I found that, I say I should have started doing these things like, I don't know, 5 years ago or something. So again, I will say, if the recommendation is never use a floating point for money, is the other recommendation is never use strings for IDs. I actually like raw types are most of the times are really a bad idea. Even in the project I'm working right now, we have a lot of for the communication with our system, we use protobuf, and we are using the compiler we're using for Scala for protobuf. It allows you to put like custom annotations, and actually I'm generating also the protobuf stubs in Scala with the IDs too. So we even went to the protobuf to get the also with IDs, and that is saving a lot of time and avoiding mistakes. I'm really grateful for this, and it's very simple change. I mean, and basically the wins for this are really amazing. So again, totally recommend this. Again, if you're there's some corner cases that uneval boxes, but opaque types no. Obviously, new type in Haskell either doesn't box. So the runtime cost is minimal, but the wins in safety are incredible. So I'm become a huge fan of this. I will never use like just raw strings again. And if you generalize that, you can use, in many cases, you should use phantom types to type check state. Depending on how critical, I mean, for some simple things you don't really need it, but for critical areas of the code, when it fits, I would recommend. This is kind of a generalization of the using IDs. A phantom types is a type parameter that actually is not used in the body of the function, but since it's there, the compiler checks it. So it allows you to create a code like, okay, I can only complete a withdrawal that the type it has is in progress. Basically, you encode the state machine in types. You put that type as a parameter of the functional object you want to process, and the signature of your method or your function only works on the object at that determined at the fixed state of that, and so you cannot. It basically won't compile if you try to complete a request that was not initiated. And using it everywhere can be cumbersome, but in some critical paths and some like areas that are when your correctness is the biggest requirement, you should really use it because the payback is great. I should have written this example also. But yeah, if you're in Haskell, like new type everything. In Scala, you can use any val or put like type parameters. But the main goal without this is, and it's something that I try to focus every time I'm writing code and functions, is like find the type signature that prevents you to write the wrong code. And that's why we have the type system helping us. That's why we have this kind of techniques like new type, phantom types, using IDs and everything. Try to find a way that your code cannot be wrong, and basically that helps a lot. I mean, when you have under pressure to write the correct thing, if you already have your like foundations laid down in a way that you cannot assemble the wrong things, it's better. I mean, I do a lot of mistakes, so I want the compiler to help me to prevent that. So every time I write a new function, I think a new type, I'm thinking, okay, basically I'm thinking, okay, how am I going to screw this? Where is the parameter I'm going to miss, or where is the parameter I'm going to put in the wrong place, and things will break up. Okay, here, okay, and then I put that in a type that prevents that. I'm trying to basically I'm fighting with my future self to figure out what is the best the way I'm going to break this down. But with this helps you. This really helped me to find out where I'm going to screw it, and yeah, I prevent it as much as possible. So basically, again, it's the same message. The more we can rely on the type checker, the better. And this is obviously, and that probably is like almost useless to say in a functional programming conference, but it doesn't hurt. In this case, it will save you from costly mistakes. On the other hand, it will make your compilation time longer, but it will really help you. It will basically have your back. Another thing I want to mention in correctness is our DSLs, domain-specific languages. This is sometimes a fashion. It comes and goes, and DSLs get really popular. Then there is this like a blowback against that, um, and then come again. I'm not. I mean, in functional programming, usually there's two lines of DSLs, like interpreted DSLs when you write a small interpreter, and there's those are the external DSLs. You can write it in xtext and then you parse it, analyze it. But usually we work in embedded DSLs. Basically, DSL is embedded in your code. There's a lot of work on that. You use basically the language compiler to compile your small language. Again, there is two lines. There is like a how do you call it? Well, oh yeah, you had the shallow embedding where basically you create functions that start you interpret your DSL as functions, or there's a deep embedding when you create the first the abstract tree of your DSL and then interpret that tree. Interesting, if you take that, if you want to add a monad to that, in one side you end with the shallow DSL, you end up with the, I think it's tagless final, and if you want to use like the abstract tree, you end with a free monad. If I'm not mistaken, feel free to correct me later. But all this is just why writing this. This is fun and everything, but especially in financial system, you work with guys that are used to complex things. They don't understand the programming language, but they can understand things. So not really a DSL, but one thing I'm been doing lately is all the calculations, instead of having all the calculations scattered across the system, is just collect all the different calculations in only one place and try to clean up in a way that is the most readable possible way. Try to eliminate the noise. So there is something. It's a page I can print and take it to the financial analyst and say, okay, how these calculations look? They are correct. Check those calculations, and they can really spend a little time like figure out that if the calculations are okay. That is way better than getting all things scattered around and trying to translate one formulas from one place to another. So I'm trying to get. The goal is to have all the formulas in one place, so very easy to review by non-programmers. It's not really a DSL, but it's something like an isolated part in speaking like a mathematical language, not a programming language. Obviously, I don't have a lot of experience with that, but it's a lot of places where like using DSL either embedded or external to validate contracts. Contracts is very there's a huge area, especially all these complex financial products has complex contracts that some can be machine checked, and there's a lot of lines of work on that. This is a Scala example. It's a little noisy, but a Scala example of one of the calculations we have in our system. Something I can try and show the business analyst and try to validate that I put all this in only one place. Like in this case, is the unrealized P&L and takes a position. It takes a mark price as a decimal, the funding rate as a funding rate, and returns a big decimal. So we got the position. We mark to market the position. Basically, is calculate the actual value of the position and then the entry value and the unrealized funding. In this case, the signature is a little better than the original one. There's no strings, there is no floats or double. And I still have work to do on this. This is still a little noisier for me, but I think like aiming to having all this in only one place, so you can basically print the page and tell the guy, okay, review this, is a great idea. In the case of contracts, there's a lot of examples around. I found this interesting. Using this is using Haskell to create a small DSL to validate trade. Yeah, basically to validate the trade contracts and operate on that. Just a small reference. There is a lot of areas on that. And so that takes me to the next big area. But I'm not going to say that a lot of this. I mean, because composition is basically the bread and butter of functional programming. That there is a lot of abstractions to work on that. All these, the category theory references we have always are all dealing with composition. I say category theory is like the math of composition. But I just going to say silly things, but like just the basic things like functor and monad, nothing really esoteric. Just with this, you can get a lot of mileage to compose, especially to work with, to assemble your functions in a way that is more readable and deal with your basically all the things is we're trying to get a more readable program that works. So one of the most useful things is like basically a map and bind, or map and flat map. Use it everywhere. You almost stop seeing them. It's just assume that it's there and start composing things. One interesting area. I have a friend working on that, using a lot of is validations, using applicatives, applicative functors to validate. Usually, the normal way, if you use a monad, it basically means stops in the first validation. But with applicatives, you can do all the validations and get all the accumulated results. And even this is a technique that everybody knows. It's really worthwhile to go deep on that, because it makes your code way more clearer. And yeah, you can start creating small validations functions and start just composing and applying and get other results. Especially when you have a user input, like a big chunk of a form, and you apply a validation for each part of the form. Then you can assemble different forms and have the same validations apply. But probably, I mean, you all already know that. It just it's just the things I wish somebody had told me before. Another thing that it was a huge success for me is using basically asynchronous code. Is in Scala, mostly that I use for work is we can use either Scala features that have some issues, but are always there. We use also like Monix and Cats.io, and having this like monadic syntax in a way that, okay, composing asynchronous function is just like map and flat map, makes work with code that deals with asynchronous is very, very easy to read and and to execute well, to execute the dependent runtime. And you can also like fine tune your thread pools based on the load you expect. But it makes work with things like with asynchronous code it makes very easy, very smooth, great experience, great programming experience. So again, it's something silly, might be obvious, but it's really great. Sorry. Yeah, and the final thing I'm using a lot in our systems is streams. That means something we have a constant input of data, and I want something to react to that. In particular, in financial system, there is a lot of like data sources that are obviously sending data. In particular, some example is you have a constant stream of market data, and you have update on prices, update on rates based on the status of the system, the amount of money you have, and for that you have a constant stream of that, and you want. We're going to give a small example of, because with that you want to calculate risk. One of the features, I thought that financial systems deal with money, but actually they'll deal with risk calculations most of the time. So you have a way, you have a stream of data with the market prices, with the rates, and we want a constant update in the risk of the system. And with a very small example, it could be like, okay, you have a price ticker that says you the update prices. You have your book when all the trades basically you have it's a group of trades, basically positions if you're dealing with futures. For that, and then with the new price, this is a process that executes constantly. In an exchange, you will decide this to see if the user has enough money to keep that position open, or you have to close it. And if you don't do this on time, you're probably exposing yourself to a lot of risk and problems, because if the market crashes or something, you will hold in the bag. So basically, this is an important process. So basically, you get the new price, you get all the positions that have, based on for the asset of that price, you calculate the risk for every position, then you aggregate the risk, and you have your overall risk for that position. This is something that they execute constantly. And in this, I have this is an example using Monix that is very close to the code we have in production. In this case, we're going to use we can consume the price from Kafka. That price will come in JSON. We parse the JSON as a mark price, then get all the positions, then calculate the delta for that position for that price. Actually, these are functions that are queried, so there is the parameter here is the position. Then reduce all the risk to only one risk and store that for the current risk for that book, so other systems can act on that. And this could be a very simple example, but I really like the way that process can be writing in a couple of lines. You can read it. It's like you can read every step, like first parse from JSON, then get the positions for the book, and then for each position with that price, calculate the value, then accumulate the value, and then store it. It's very easy to follow the steps. There is this is a whole stream that you can tune at runtime. You don't need to read to deal with kind of batches okay, or blocking, or okay, if I read this, I have to wait, or all things are easy, clear. I mean, the intention is clear. That's the thing I really must enjoy of this. I really like working with streams. There's a small example that is actually not that far from what we use in production. But I just wanted to show that our system, you have your core system, and then it's surrounded with this kind of streams operating on values and updating like kind of the global state. So in conclusion, do I have a conclusion? I'm not sure. But yeah, an approach using functional programming for this kind of system, because they deal with a lot of data. They have a very complex logic. They have big performance requirements, and also you definitely want correctness. And every of these challenges is tackled by one of these features, like the complex logic and the correctness. We have type system to help us tackle that. Again, for the logic, we have composition, and for correctness, we have composition. We have two things that we know that are correct, and then with our the way we compose things, we know that it just will be also the composition is correct. And dealing with all of data and performance using data streams, it's not a specific technique from functional programming, but it's really, really close to the spirit, and makes things very easy to read. And basically, it's lazy data structures operating with map and bind. That's kind of the essence of streams. So in conclusion, okay, probably I'm preaching to the core, but still, I mean, there are hard lessons. I'm still kicking myself on not doing some of the things earlier. Most of the techniques here will save you when you're in the bind. If you already use these kind of things, it will help you. Yeah, not only from financial system, but I would say that here the pressure to use these kind of things is higher. But yeah, hopefully you're using them and having success too. With that, I would say thank you. Really, thank you for listening to me. Hope you enjoyed. I really like it, and hopefully also we're gonna do it in a better way. I'm free for comments, suggestions, insults, whatever.
Thank you so much. We've got a couple of questions in the chat box there, if you can see that. And then we've got one in the Q&A section, so you can answer them if you...
Okay. Okay, how the DSL helps you maintain correctness? Do you mean it's more readable? Yes, there is two things. DSL obviously is machine check, so the compiler knows. Obviously, the compiler will check that it's correct. And but the main thing about DSL is like it's a code that it should be readable by non-programmers. It's something for the domain experts. Basically, it's code dressed as a domain language, so the experts can understand and figure out the ways you're screwing up. That's kind of the whole point.
Cool. And you've got some questions in the chat section as well. Oh, and another question in there.
Okay, yeah, yeah, it was, yeah, sure. I will share the presentation with the code later. Yeah.
Cool. And in the chat section as well.
Uh-huh. What libraries I'm using for data streams? In my core system, I'm using ACA streams, but also I'm trying to move to Monix. There is also, because the queues are Kafka. There is a Kafka source for Monix, but all the streaming libraries work relatively same. Depends on your preference. But yeah, I'm using either also ACA streams or Monix.